Got so caught up with a few things ready that I forgot to edit this. So last class we were talking about, starting to talk about cyclic peptides, different ways to stabilize peptides. So we talked about peptoids, we talked about unnatural amino acids, we talked about beta amino acids, and then we started discussing cyclic peptides. So I want to move on and discuss that further. And then the other thing was we started discussing, I said that, hey, I posted all these resources to the Blackboard and realized I'd actually posted them at the beginning of the course. So a few review articles on different forms of click chemistry. But we'll finish off with cyclic peptides first. So where we left off, we were discussing these different forms of cyclization. So if we have side chains along the peptide that contain amino groups or carboxylic acids, those can cyclize to give us a cycle within the peptide. And if we have just guys on the end, those can cycle to give us a head-to-tail cyclization, which means that there's no dangly bits. Whereas if we do anything with the side chains, we have dangly bits. So you have these kind of loops, and then you have sort of straight chain sections. Those, of course, the straight chain sections are still sensitive to exopeptidases. There's all sorts of things you can do to reduce that by, for example, incorporating unnatural amino acids or peptoids or unusual end caps or end groups onto the peptide. But maybe you just want a normal peptide because you're doing some biological probing or you're trying to investigate something in vitro, in which case it's not going into an animal anyways, so you don't need to worry as much about the stability of the peptide. You really want it to reflect reality. So there's all sorts of reasons you might use these different types of cyclic systems. But, just the top of my head, that's a little weird. But sort of like the most common form of cyclization in peptides, like the most common form of cyclization in proteins, is disulfide bond formation. So if you have any peptide, and this is like how, so except for a few marine organisms and things, the sort of peptide bond cyclization is very, very, very unusual. Like having cyclization through an amide bond is unusual because a ribosome can't do that. A ribosome makes linear peptides. It doesn't make that amide bond. And amide bonds don't form super easily. You really do need to help them out. Like they don't happen spontaneously. And so you need an enzyme for that. And us mammals don't really have a lot of great enzymes for doing that other than a ribosome. And as I said, that makes linear peptides. So a lot of these sea sponge living bacteria do have extra amide synthases, I guess, which will connect up a carboxylic acid and an amine and make an amide bond, and they'll do it on a cyclized system. And they use those, as we discussed, as antibiotics against other bacteria in the unending war of bacteria on bacteria warfare. But if the most common form of cyclization, definitely in eukaryotes, is disulfide cyclization. And just in case you forgot what cysteine looks like, I'm going to abbreviate just like SH coming off the peptide because it's the only thing that has that. But we can also, draw it out real right, like sorry, my allergies are acting up. Don't know why. I was in Toronto on the weekend and that's probably it. Allergic to Toronto. Okay. And I drew my peptide backwards. So we can have these two cysteines, and if we treat that, all sorts of conditions, but it's basically just oxygen gas. If you take DMS, if you dissolve your peptide in solvent and pump in oxygen, your cysteines will cross-link. Your sulfurs will cross-link. So we'll end up with sulfur-sulfur single bond, which is just a little weird. But of course, this is a disulfide bond. There's all sorts of ways you can do this. If you look it up, you'll find all sorts of fancy-ass catalysts that get used to make this disulfide bond. It's unnecessary. And you make a ring. Now, the problem with these, of course, is they're reversible. It's easy enough to cleave that disulfide bond as well and revert it back to two cysteines. And so it has limited utility if you're trying to make a very, very stable cyclic peptide. But if you're trying to imitate biology, biology makes its cyclic peptides to disulfide bonds. It's what it does. That's just how biology works. So yeah, information. But that's not typically how you would try and do it synthetically, because again, there are a lot of cysteines in peptides. Maybe you want the cysteine doing something. So we want other tools to make disulfide bonds, or sorry, not disulfide bonds, but we want other tools to make cyclic peptides. So I want to posit a question here. Let's say I have two rings here. One is 4 amino acids, and one is 30 amino acids. Which one of these rings of amino acids? And a ring of amino acids is a cyclic peptide. So which one of these is harder to make? Is it harder to make a ring with 4 amino acids or a ring with 30 amino acids?
Four?
Sorry, Hazel?
I'm thinking maybe 4 is harder because of the strain, but
Yeah. Yeah, it is. And it's counterintuitive. Because often we think, okay, 4 amino acids is only, I can do math, is only 12 atoms long. 12 atoms trying to cyclize into a ring sounds much more reasonable than 90 atoms trying to cyclize into a ring. Just on thinking about this, because if you can think about something 12 atoms long and wiggling around everywhere, it's more likely the ends will bang into each other than 90 amino acids bang into each other. And that's the organic chemist in me speaking, and it's wrong. And it's because peptides want to elongate out, like the peptide bond. This thing. Whatever. Guess it should be up. And these four atoms want to extend out from each other. And that's because, of course, there's a resonance between of the amide bond So these four atoms are kind of forced into a line, stretching out. And now it's really hard to wrap that back around to meet the end, because the next four are going to be all stretched out into a line. And the next four. So the whole thing, peptides tend to elongate out into a line. They don't tend to want to cyclize and curve back on themselves. So when you have 30 amino acids, that's usually a lot easier to do than with 4 amino acids. It's really, really hard to do with a small number of amino acids. And how do I define small? About 3 to 7 amino acids. It's a lot easier at 8. And at 8, suddenly, 8's kind of like the sweet spot where the things aren't very far apart, but you have enough flexibility in it that it can spin around and form a ring. But the smaller you are, actually, the harder it is. And for 3, you can almost think of it as like a triangle, because they're almost pretty rigid, the amino acids. And so it's actually pretty hard to make that triangle. Everything's always about geometry in the end. So this is hard. The interesting thing is, if you have 30 amino acids in a ring, your ring is floppy, right? You can imagine the whole thing just kind of flops around in all different kind of conformations and configurations, because there's a lot of flexibility in there because there's 30 freaking amino acids. Whereas if you only have 4 or 5 amino acids, your ring isn't floppy. It's very static. And that's because there's very few ways the bonds can bend themselves to minimize strain within the bonds, while at the same time minimizing angle strain around the entire ring to try and keep the entire ring, reasonably well shaped and not torsioning it out into weird angles and things. So the smaller the ring, the more defined the form. And if I want to make a drug, or I want to make something that has a defined shape to do catalysis or drive, or do something very specific, shape is function. Like if something has a function, because of its shape. And yeah, all the chemistry that goes on, making sure you have nucleophiles and electrophiles and acids and bases, that's all important stuff. But if your shape doesn't fit, it doesn't matter. And so if you have a very small ring, you can have a really well-defined shape. So a lot of drugs are on the smaller side of these peptide rings, not on the bigger side. Again, because they just define the shape better. So here's the problem for you. And we're going to talk about maybe 4 ways we're going to solve this problem. Let's say we have a peptide. We'll make a nice easy peptide. By easy peptide, I mean no silly functional groups. We got 4 amino acids. What do we have? We have a glycine, a phenylalanine, aspartic acid, and a valine. I think that's aspartic acid, maybe it's glutamic acid, I can never remember. It's aspartic acid, good. Okay. I want to cyclize it. I want to cyclize this onto this. How would I go about, what do you think the problems are that we need to think about with this when we're trying to cyclize this? And how would I go about doing this?
So instead of cyclization, it might be intermolecular.
Right.
And I'm trying to think of a solution of that.
So it's a lot easier for one of these molecules to react with another one of these molecules than to cyclize on itself. Because again, 4 amino acids, really hard for it to bend around. It wants to extend out like this. That acid is generally saying nowhere near this amine. So what it wants to do instead is interact with amine on another molecule because it's extending out, right? So it's going to find another molecule, and then we're going to have 8 amino acids. Then that might cyclize. But I don't want 8 amino acids to cyclize. I want 4 amino acids to cyclize.
Another
Is that what you want to say,
group,
Ronas?
another amine group in this amino acid can cause a problem.
Which other amine group? The other
It
nitrogens
doesn't-
are all amines. They're not amines, so they're not
Amine.
nucleophilic.
Oh, so good.
Because like this is not going to react because the nitrogen is tied up by resonance
Yeah.
with the carbonyl,
Yes.
and so it's non-reactive. So we don't need to worry about that. If we did have another amine on here, if we had a lysine residue, that'll be a problem. And note we have a protected carboxylic acid, so you're not wrong in thinking about that problem, because that's why we need to protect this. Otherwise, this carboxylic acid would compete with this carboxylic acid. I think fundamentally, this is the problem. Short peptides want to oligomerize. Not cyclize. So how do we solve it?
So if we can find the right enzyme that can just bend the peptide to force it to make a ring.
That would work. Find the right enzyme. How much time do you have?
What's that?
How much time do you have to find the right enzyme? I think this is definitely doable. I think you could probably spend the next 50 years doing it to cyclize this one guy to find the right enzyme. Because I'm sure that enzyme doesn't exist. Now, you could definitely design it. And I actually think I don't mean to make fun of you over this answer because you're right. I think in the end, this is how we are going to do this. Like if I was going to teach this class in about 2070, I will say, yes, of course you pull out your designer enzyme that you just programmed and it cyclizes your peptide. Like, why would you do it any other way? Enzymes are always the best way to do things. I completely agree with you. It's just finding an enzyme that cyclizes an unnatural amino acid or a never before synthesized peptide is going to be challenging. But I agree that it is definitely the best way. So I'm going to say this is the future. And I do think that's actually an incredibly valuable thing to be doing and looking into. But if you want to do this right now, that's not going to work. But I agree with you completely. It's the way forward. So any reaction, what is the, let's just think about this. What is the rate law for the intermolecular reaction that where you have a oligomerization?
There's a rate for that?
There's a rate law for everything. What goes into the rate of a reaction? Let's say I have a simple reaction. A plus B goes to C. Like, I'm not asking for a number, but what does the equation look like? Rate equals a constant. The constant tells us talks about the reactivity of the species. Says how nucleophilic or how electrophilic something is.
So I would guess the constant of the amine group times the constant of the carboxylic acid.
Yeah, that's all incorporated into this constant. All the constants are in there. What else matters? I say, hey, I've got concentration. So the concentration of A and the concentration of B. That's a standard rate law for a bimolecular reaction. Because if you increase the concentration of A, you increase the reaction rate. If you increase the concentration of B, you increase the reaction rate. And if the the rate determining step is A bumping into B, then this is the rate law. The rate law basically explains what happens in a rate determining step, what molecules are involved. Okay, so if we talk about the intermolecular, the oligomerization one, what goes into the what goes into the rate of the oligomerization reaction? What's in the rate determining step? What needs to come together? We'll call this A.
N terminus and A C terminus.
Oh, different
Okay.
A's or the same A if we're oligomerizing?
To end of each molecules that we have.
So we need one A and we need another A. So we need two A's to come together in a rate determining step because we're oligomerizing. So K equals A squared, concentration of A squared. Okay. Cyclization, rate equals K2, we'll call it K1. What concentration matters for cyclization rate?
This one we need.
Concentration doesn't matter.
Nope, be careful. So the amount of time it takes for one molecule to react, the concentration doesn't matter. I agree. If you think about one molecule in isolation, this is actually a really interesting question because it came up on the comprehensive of my PhD, where one of the professors in my department at the University of Ottawa basically said, so for a unimolecular reaction, why does the concentration matter for the rate? And because in unimolecular, so it basically say it this way. So in a unimolecular reaction, a molecule reacts within itself. So it's only the molecule doesn't depend on any external interactions. Therefore, in a unimolecular reaction, why does concentration matter in the rate? And he asked that to us, and he also asked that to all the other organic professors in the department. And none of them got it right. They got it right after thinking about it for a long time. But why does the concentration matter in a unimolecular reaction where nothing else matters except the molecule reacting with itself?
Is it actually, I'm thinking it's not about bumping into each other because that doesn't happen when it's intermolecular. It's more about its efficiency. So higher concentration you have, like there are more molecules that can react with each, react to themselves at the same time.
You're on the right track. What are the units for a rate?
Unit, concentrate. So the what's a concentrate, the unit of concentration square? So
Well, yeah. Well, rate is measured in moles per liter.
Yeah.
Per second.
Oh, wait.
So that's a concentration. So we're always measuring, because we don't measure how long it takes an individual molecule to react, because we can't do that, because we can't see individual molecules. What we're measuring is how long does it take a volume of molecules to react. And so if I have one molecule in a vast sea of solvent, it will react over a given time frame. But if I have 10 molecules in that same sea of solvent, I expect a molecule in that amongst those 10 molecules to react a whole lot faster than a one on its own, because now there's 10 of them that can do this. So as you increase the number of molecules in the solution, as you are exactly just saying, you increase the chance that any one of them is going to react. And so the more molecules you have in solution, because there are more molecules, at any one time, more of them are going to be reacting because there are more molecules, even if they're not dependent on each other. Rate is a function of, it's a concentration per second. How fast it's not molecules per second, it's concentration per second. And so that's why rate does depend upon concentration, even for a unimolecular reaction where it doesn't matter what else is going on, it only matters about that molecule. It's because we're not measuring rate in the half-life of a given molecule. That's a half-life. We're measuring rate as number of moles per liter that react per second. Anyway.
So it's actually like the normal distribution. There's someone
yes,
okay.
Exactly.
Yep.
All thermodynamics and kinetics are statistics. So it's all a normal distribution, where there's an average rate for a reaction. Like there's an average time, there's a half-life for a given reaction. And at that point, half the molecules will have reacted, and the other half won't have yet. And if you have 1 million molecules, 500,000 will have reacted by that time. If you have 2 molecules, 1 will have reacted by that time. But our rate is molecules per volume, and so you're going to have a higher rate if you have a lot more molecules present. But the absolute speed of the reaction, the half-life of the reaction, is independent of concentration. But that's not what we're talking about here. We're talking about rate. Anyway, so that's why concentration shows up on rate laws of unimolecular reactions. But, okay, so taking this into account, and we know that K1 is much, much bigger than K2, because oligomerization is faster than cyclization. Okay. So if A equals 1, for example, let's say K1 equals 10 to the 7, K2 equals 10 to the 2. If A equals 1, if it's 1 molar, 1 times 1 is 1. K1 is 10 to the 7. So this would be equal to 10 to the 7. Whereas this would be 10 to the 2 times 1 is 10 to the 2. 10 to the 7 is a lot bigger than 10 to the 2. So you get oligomerization at a concentration of 1 molar. How can we favor cyclization?
Half the concentration.
Yeah, decrease the concentration.
Decrease the concentration.
So let's say instead of A being 1 molar, because K is a constant, right? It is a constant. Let's say A equals 0.000001 molar. Now I take that and I square it, because A times A, I need 2 of them to come together. There's my calculator. 0.000001 squared. My calculator tells me that's equal to 0. So I'm going to do a less that drastic one because I don't have enough digits on my calculator and I can't be bothered to switch to scientific notation. 0.00. Therefore, A squared equals 0.00000001. So now if this is just K2 times A. K2 is 10 to the 2. A is 0.001. That's going to be 0.01. Now do it in a different color here. Whereas this one is going to be 10 to the 7 times this number. It's going to be 0.1. So it's still faster. So we're going to need to go lower than that. But we've closed the gap from 5 orders of magnitude to a single order of magnitude. Keep dropping the concentration, you start favoring cyclization. I hate this confusion of English. So a low concentration is a high dilution. You dilute it a lot. So it's high dilution, but it's a low concentration. And cyclizations are highly favored at low concentrations. Okay. The next way we can avoid this too, and my preferred way, this works, but the problem is you can start getting humongous, like basically taking rain barrels and doing reactions in rain barrels and getting 10 milligrams out. It works. It works really well. It's just you need so much solvent. So the second way is, what if you can physically prevent oligomerization? You can physically prevent 2 molecules from coming together. And how can we do that? Well, let's step back to thinking about the solid phase peptide synthesis. So we drew this like this with beads coming off, and we sort of think, and I draw it like this with the bead and these things. But remember, what we're really doing is the bead is huge. There's a hole in it, and there might be a few peptides kind of coming out from here. Now, if I can keep the peptides a low enough concentration, I'm going to delete you, going to delete you, going to delete you. Then the peptides are far enough away from each other that they can't interact. And so if I try and cyclize this peptide, it can't oligomerize because it can't see any other peptides because it's stuck on a bead. And it can't interact with another peptide. It's too far away from the other peptides. That's cool, you might think. Okay, that's neat. But that doesn't help because I need to attach it at the carboxylic acid terminus. And I need to cyclize the carboxylic acid terminus, but you just told me I'm attaching at the carboxylic acid terminus, and I can't cyclize if it's attached there. That's all absolutely true. That's why it's really, really handy. In this example, we have a side chain, carboxylic acid. Nothing is stopping you from immobilizing your peptide on the side chain and using the side chain carboxylic acid to attach your peptide to the bead. So I'm just going to write this out. AF aspartic acid. I do not remember off the top of my head what the code is for aspartic acid. It's not K. D. And valine. So we have AFDV. And what we're making is AFDV. Right? Cycle. I drew it AFDV, but if I'm cyclizing, who cares? AFDV is the same as DVAF, and I'm making the bond between F and D. Or VAFD, or FDVA. These are all, I can make them any order I want. I'm making it into a ring in the end. Rings have no beginnings or end, so it doesn't matter where I start. So if I can immobilize D onto my bead, seems like a good place to start. So what I can do is I can protect the alpha. Yeah, I'm putting it over here. And we can use a Wang resin, for example. Look back through your notes. It's a Wang connection. Cleaves with strong acid, like TFA. We protected the carboxylic acid. We have an FMOC. We can just use standard solid phase FMOC chemistry. So again, that's one is deprotect. We deprotect FMOCs using 20% piperidine and DMF. I'm going to, how do I do this? I'll send out an email to students with a book on FMOC solid phase peptide chemistry, which can act as a reference for anything if you're working through assignments and things. It's a good reference to have anyways. So it's a great reference for this. I think it's the best book that's out available. And then we couple. So let's say it's just, I don't know, HCTU. This is D. The next amino acid I need to put on is V. And I guess it'll be FMOC VOH DIPA. It's my coupling agent, my amino acid, my base that I need for that coupling. And that's going to then add my valine. Not going to draw them all out, we'll just do this first one. Just because it doesn't hurt to have a few more examples in the bag of ways to do these. So again, we have the bead here, we've added the next amino acid. We can then add the next amino acid and the next amino acid, and we end up with it's V, then A, then F. So I'm just going to draw in the carboxylic acid and the bead. Okay. So now our peptide is separated from all the other peptides. I shouldn't have used Wang resin on this, or I shouldn't have used a terbutyl group because I want to selectively deprotect it. I'm going to switch. Sorry, I'm going to switch to a benzoyl group. And the reason is that I can now deprotect this and this. So I use hydrogen gas and probably a soluble palladium source. If I use palladium on carbon, it's just on a solid support, and I'm trying to react something on a solid support with something on a solid support, and that never goes well. So palladium acetate. And then also, you know, piperidine DMF after that. So I'm not going to touch the resin bead. That's still intact. But I've liberated up that carboxylic acid, and I've liberated up this terminal amine. And now they have no choice, because if I try and cyclize this, so let's say I treat this with, well, let's use the same conditions we used up there, HCTU, DIPEA. This peptide can't reach any other peptides because it's stuck on a bead. So it doesn't matter. So this is kind of like that concentration thing, except in concentration we're avoiding molecules bumping into each other by making it very unlikely for them to bump into each other because there's so few of them. Here we're making it literally impossible because the molecules do not have freedom to move. They can't sort of leave the bead and wander off and interact with other beads and other peptides and other things. So the only thing the peptide can do is cyclize on itself when it's on the bead. And it's called on-bead cyclization. Very powerful because you don't need to worry about super high dilutions. And you're making peptides on the bead anyway, so who cares? And at this point, that's still attached to the bead. Then we can cleave it from the bead just using TFA. Strong acid. That's going to cleave off the carboxylic acid. It doesn't matter if it was a side chain or a main chain carboxylic acid. It doesn't either way. This, by the way, this is one of the questions on one of the assignments. And you get your product. So by carefully designing where you want the bond to be. That's great. Okay. So another thing we can try and do to solve this problem is, sorry, brain not working properly, is I said that, the issue is that these peptides elongate out into long chains. That's true. There's one exception. And that's proline induces turns. So normally an amino acid elongates out. If you have a proline, it induces a turn. So if you want to make a small ring and you got a proline in it, suddenly you've got somebody who's forcing you into kind of a ring shape. So small peptides with prolines make rings. Easy. And that's wonderful if you have a proline in your sequence. If you don't have a proline in your sequence, it's not that helpful. But there's a way around that. Because what's important here is that it's less sterically hindered for this to fold back on itself than it is for itself to interact with the ring. So it's this whole idea that we have this 5-membered ring that kind of locks things out and doesn't allow it to extend out. It wants to fold it back. If we can fake that 5-membered ring, then maybe we can add other residues to this whole proline thing and make use of this strategy to make small rings. And that's exactly what we can do. So this is using a strategy called pseudoprolines. They're not prolines, but they're kind of like prolines. So the three that we see, so if we, again, I'm just going to draw out proline again. But let's think about 2 other amino acids. Sorry, I don't know what I'm drawing there. That's just wrong. It's off. The nitrogen. It's like that just doesn't make any sense. So this is serine. What somebody noticed was, wait a second. If I can stick another atom right here, I can close that ring. I can get the oxygen attached to it, the nitrogen attached to it, and I can get a 5-membered ring. I'm not going to talk about how to make these. If you want to look it up, it's very interesting to me. Weird definition of interesting. I completely accept that. And it's actually really, really cool. And you can sort of think about the possibilities very quickly. But we can tie those up and you get the same effect. So you can get these pseudoprolines from you taking serine, using the nucleophile and the oxygen and nitrogen. You can then make your peptide, and then you can use an acid. You don't need a very strong acid. Again, TFA, some water. Essentially, if you go back to our sugar chemistry things where we talk about cleaving acetals and isopropyridines, same diff. It's got nitrogen here instead of an oxygen, so it's even easier to cleave, and so this comes off really fast. So if you use the right amount of acid, you can just cleave this off. You liberate it back to serine. So the cool thing is, you put in this fake proline, you use that to make your turn, and then you got serine back. So you can cyclize when that pseudoproline is present. So you make your your peptide chain with a pseudoproline amino acid, like a serine, or you can also use threonine because it's basically the same thing. And the other one you can do, of course, is you can do cysteine because it's like that, but with sulfur. So one of the things that my research group is doing is actually trying to extend this strategy to all the other amino acids. So we're not because even here, even though this is a lot more flexible than just having proline, it's still only 3 of the 20, and with proline 4 of the 20. It'd be really, really nice if we get another dozen or so. So we get these up to like 16 of the 20 amino acids can be turned into pseudoprolines. But for that, you do need to start messing with them pretty heavily and figure out how you're going to get rid of them afterwards. Which is a challenge and fun, but it's opening up the avenue of being able to make basically any kind of small cyclic peptide. Because as much as fun as it is to do the on-bead cyclization, that only works if you have a glutamic acid or an aspartic acid in your sequence. And if you don't have those, you're screwed. Just like the pseudoproline thing only works if you have proline, serine, threonine, or cysteine. If you don't have those, you're screwed. So there's still a lot of places where you're screwed. And it would be really, really good if we reduce that space where you can be screwed in down to a much smaller space of really inaccessible sequences. So we can make more and more and more of these. The last 2 things I want to talk about with the cyclization, so I guess we're just finishing with cyclization today, is I wish this didn't work as well as it does, because it's just so simple and it's embarrassing. So we can use a templating strategy. This works really, really well for about 5 amino acid rings. And the way it works is, let's think about what our problem is here. It's the same one we've been facing. I'm going to just write leaving group on his side. Some activated ester, HCTU, DCC, CDI, whatever your favorite activated ester is. Doesn't matter. We'll throw in a histidine for good measure. I got confused at some point there. That's where I got confused. So if we're trying to cyclize this, again, we have this problem of this thing wants to extend out. So in this case, we don't have any pseudoproline candidates. No serines, no threonines, no cysteines. We've got no side chain carboxylic acids. So we've got nothing we can do the on-bead cyclization. So this leaves us with the idea of going, okay, I guess I'm going to have to dilute this massively and hope for the best. And what somebody realized is that, wait a second. What if I dump in a ton of salt? Like just so much salt, so much sodium chloride. Okay, I don't see how that helps. Well, if you have enough sodium, sodium forms complexes with carbonyls. So, add a little bit of sodium. Ooh, it interacts with that carbonyl. Things rotate around a little bit, and then this carbonyl starts interacting with that sodium. And so what did I just do? I just bent the whole thing. And so now extending out, there's kind of a sodium here, which is interacting with both of those. Then, of course, this guy sees the other guys are having a party and it joins in. And it's going to bend this guy in. So now what you're noticing, what we're doing is, instead of this whole thing extending out, we're starting to actually rotate. And because 1, 2, 3, 4, 5 kind of brings us back into a ring, and now this nitrogen is really close to that leaving group, and we cyclize. It's best for 5. It works okay for 6 or 7. It's still not amazing. Works really well with systems like this where the primary amino acids are mostly hydrophobic. It doesn't work great when they become hydrophilic because then they start competing for the sodium and the whole system falls apart. The examples where this has worked are beautiful. The examples where this has failed are not mentioned in the literature because nobody ever wants to talk about their failures. So when it works great. When it doesn't work, it's miserable. But it is a different way we can think about trying to cyclize this. Can we force this thing to form a ring? And those of you who know about like crown ethers, we're starting to make something that looks a bit like a crown ether here too. These oxygens are all associating around the anion, and it's actually very, very similar to crown ether kind of chemistry. And that's where it was inspired from. The last thing I want to discuss doesn't actually help cyclization specifically. It's just kind of cool. It gets used in cyclization. While starting or ligation. And it's because one of the problems with cyclization versus oligomerization is even when you're highly dilute, if you need to make a small ring, the strain on the ring is pretty high. So traditional chemistry, amide chemistry, doesn't work amazing. Like it works less well cyclizing than oligomerizing because you have to strain to get the angles right. It's kind of tricky. So this gets around that. So it does, if you have, I'll show the mechanism of this, but basically if you have two identical reactions, one set up to do a Staudinger ligation, one set up to do one of these macrolactamizations, which is what we've been doing, making amide bonds, or lactam, cyclic amide bonds. And everything else is the same. So concentration is the same. You'll get more cyclic molecule from the Staudinger than from the lactamization. And that's just because the Staudinger, the angles are better. It favors cyclization a bit more. Because it's a little bit more sympathetic to the angles that are involved when you're trying to make those rings. But anyways, this is really, really, really cool. So you take a peptide, just a normal peptide. You have made a peptide. So the first thing we do is we do what's called a diazotransfer reaction. We take triflic azide, which is exactly what it sounds like. This is ridiculously reactive. And again, if we draw a resin structure of this, we get that. And so it's kind of a weird reaction in that, let's, for the sake of argument, this isn't actually the case, but it'll make us all a little bit more comfortable with the arrows I'm going to draw. Going to deprotonate that carboxylic acid. And then I'm going to use my nitrogen as a nucleophile to attack the positively charged nitrogen and break the nitrogen carbon bond, nitrogen bond. And that's going to give me my product. That does not look very stable, of course. So we're going to quickly strip away one of those hydrogens. Gone. And then we're going to lose the other hydrogen to make an azide. So we're going to go from an amine to an azide by treatment with triflic azide. So I'm just gonna write this out over here. It's a really good way of converting amines to, well, it's the best way of converting amines to azides. Okay, so we've made an azide. Big whoop, who gives a shit? Okay, next step is we're gonna couple something to that carboxylic acid. So step 2 is we're gonna use HCTU and this weird ass reagent. Thiomethyl triphenylphosphine. What does that do? Well, it's HCTU. It's going to make an S. Normally, we would make an amide with this. In this case, we're going to make a thioester with the sulfur. Okay. So I've taken a normal looking peptide and I've fucked up both of its ends. I've added an azide to one and this phosphorus thingy to the other. Why does this matter? It's because this phosphorus thingy and these azides, heat them a little bit, just a little bit of energy, and they react together very quickly. What do? I'm going to draw that arrow. So we have just a normal peptide that's now made a ring. And the bond angles on this are very, 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 very forgiving because the phosphorus pushes electrons out from the nitrogen and it pushes them away from the ring. So we don't need to actually kind of bend in with the carboxylic acid directly aligned with the nitrogen, everything kind of sterically blocky and very, very tricky. This is a lot of room. We're on the outside of the molecule. It's very, very unhindered. It just happens very, very quickly and easily. And phosphorus can make 90-degree angles, which really, really helps. So we have this thing. It looks like a 5-member ring. It's not. There's a huge freaking peptide in a way. But we have this weird situation. Now, that is a weird situation. So what can then happen very quickly is nitrogen gas can live its dream, or nitrogen can live its dream becoming nitrogen gas. So we're going to lose nitrogen, N2. Driving force here is going to put an N minus next to a P plus, which is pretty good. N minus, phosphorus plus, some triphenyls, 3 phenyl groups hanging off of here. Peptide, carboxylic acid. Okay. That's a bit weird. Now this is where the magic happens. That nitrogen phosphorus bond isn't super strong, and we have a lone pair, an extra lone pair on this one. We've got 2 lone pairs on this nitrogen. Thal ester bonds are really, 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 really weak. So our nitrogen comes in and makes the bond of its dream, which is what we want. We want to make this carbonyl amide bond, and so we do that. We break the thal ester. We are trading an amide for a thal ester. That is a damn good trade. Amide bonds are stable. Thal ester bonds suck. So if we follow that logic through, I'm now going to curve my peptide all the way around. So we have a cyclic peptide now, and it's got this dangly phosphorus, which now just frankly looks ridiculous. dangling off of it. I have run out of space. So I am going to take that molecule and I am going to draw it on the next page. I'm just going to cyclize like that now. So that seems weird. I'm not quite sure where to go from that. And that's because this now undergoes a fast equilibrium. To make the ylide. If you remember ylide chemistry, it's very stable to make positive charges next to negative charges on phosphorus. It's a very, very acidic hydrogen on the carbon, so it's very, very favorable for us to trade an S minus for a C minus here, because the C minus is directly adjacent to the phosphorus, and it's really almost making a double bond with the phosphorus. And so let's just make the double bond, and that releases the nitrogen. And now what we have is we have a cyclic peptide. So we've generated this phosphorus agent. We've cyclized our peptide. This will obviously just grab a hydrogen from water or anywhere, like it doesn't care where it's grabbing the hydrogen from. And we get our final product, which is a cyclic peptide. So why am I showing this? Makes cyclization easier and doing peptide bond formation directly. So we've talked about 4 or 5 different ways to cyclize today. So we started by discussing one way to do it is just this: dilute the crap out of everything. High dilution, take your peptide, make an amide bond using standard peptide chemistry. That works okay. The other thing we talked about was disulfide bonds. So you can make disulfide bonds. Go ahead. They're great. We're actually going to start talking about how we can use click chemistry to make cyclic peptides next class. And we're going to be using them for a lot of other things, but there's nothing stopping using them for cyclic peptides. But high dilution is one traditional way. The second way is we can use this on bead cyclization. So if we're stuck on a bead, then there's no way for 2 peptide molecules to come together and oligomerize. You don't need to worry about the oligomerization problem because they can't reach each other because they are stuck on a bead. The problem is this only works if you have a side chain you can immobilize to the bead. And if you don't want to get fancy, that means just glutamic acid and aspartic acid. Of course, you can use other things, but you need to kind of get fancy with the linker between the bead and your peptide. It's worth getting fancy sometimes, but you kind of need to redesign chemistry. Then we can use this whole idea of the pseudoprolines, because prolines induce turns. So if you can get a proline into your molecule, or if you don't care about one part of your cyclic molecule, then you can stick you can substitute one amino acid for a proline, induce that turn and cyclize them easily. Or we can use these pseudoprolines based on serine, threonine, or cysteine. So we can make a fake proline take advantage of that induced turn, cyclize, then relieve and recover the original amino acid by cleaving this dimethylacetal. The other next way we talked about was templating. So if we use a metal, normally sodium, normally 5 amino acids, we can template it because all the carbonyls start wrapping themselves around the sodium, bringing the nitrogen and the leaving group close together. So again, you probably want to combine this with low concentration to avoid oligomerization, but this will work better than not having sodium. There's no, as far as I know, there's no one has really directly observed this effect. The experiments seem to say that, hey, this works better. There's some NMR data showing that you have bond elongation in the presence of sodium, which seems to say something's happening. But this is still hypothetical. Then we discussed another way is to help that bond, that chemistry of bond closing, not be restricted by the steric strain that's involved and torsional strain that's involved in making rings. And so we can use a Schrödinger ligation, which kind of offloads it because the ring closing reaction occurs outside of traditional amide bond chemistry. And so we're not restricted by all the bond angle restrictions of amide bond chemistry, because this is where that ring closing is happening. And the bond angles are just weird from what phosphorus can do. It doesn't need 109 degrees. It can do it in 90 degrees. And so it can really, really tightly form new bonds in things where the angles do not make a lot of sense. And that can be very, very helpful. So that's where we've gone with the cyclizations today. We've done cyclizations. We're kind of done talking about peptides and proteins in isolation as well. And what we're really going to be shifting on to next is talking about how we can combine different components and different biomolecules into making new types of functional biomaterials, especially by using click chemistry, because that's really the way forward to make anything of any kind of complexity. So yeah, I think I'm going to leave it there for today. It's 9:50, so we're right on time. And I guess any questions about any of this stuff from today? Okay, I'm going to make sure I post these a whole lot faster than I have been. I noticed I was like a week behind. I'm really sorry for that. Make sure I post these slides, post the video. I will email to anyone who requests it by email a copy of a book on peptide chemistry, because I know that we're moving a lot faster through some of this stuff. So send me an email and I'll send you a copy. I think it's the best text out there. I own the text and I'm sharing my version of it, so it's legal for academic purposes. Just I'm asking you not to share it any further. Okay. Other than that, take care. I will see you guys on Wednesday. And next week we have the undergrad presentations, and next week's the final week of class, so we're down to 3 classes left. Okay, take care. Bye.